Hello guys, today I'm going to take another look at the Siku Control 32 servos, and today we'll actually have some success and be able to control the servo. So I've actually managed to get an Arduino to control one of these Siku Control 32 servos. It took quite a long time, so what I'm going to do is just show you the different steps. So the problem we had the last day was that we didn't have a controller and we didn't have the battery to power up this Control 32 control board. So there was no way to know that this was actually active. There was no lights or no nothing. But when I was at the Castleblaney show, one of the viewers came along and he gave me a controller and a battery so that I could get the model running and hopefully solve this problem. So thanks a lot, William, for the different bits and pieces that you gave me to try and solve this problem, and I don't think I would have got it done without them, so thanks a lot for that, and I hope that you'll be able to make some use of the code yourself. So once I had the battery and this infrared controller, I put the pieces of the John Deere 6920S back together. So I needed this channel select switch, a motor. I soldered a motor on here because if you can see here, I just have a hobby servo because I've already used the servo in the John Deere 6920S. So I had gutted the control board from this servo and put it into the Siku servo, which then went into the John Deere 6920S. So I had the remains of this servo, and I've just connected them up to the remains of to the control board of the Siku Control 32 servo. So there's nothing here, only the two wires that control the motor and the three wires to give us the feedback from the potentiometer. So that all goes back here. Then I have the four wires. I just put some pin connections on here so that I could intercept the signals in the middle here, and I've just rewired them back to the main control board. So now when I put the battery on the board here, we should be able to get it to move the motor. So you can see now we have control. I forgot to mention the infrared receiver is over here, so I just put them facing each other, that's all. So if you remember from the last video, I thought that the outermost wire here would be ground and the next wire in would be the VCC. Then the next wire, the orange one here, is connected to all the servos, so I thought that was most likely a clock signal, and then the final wire goes to the individual servos, so I thought that would be a signal wire, so I thought it was probably an I2C sort of bus. So with that in mind, I took a look with the oscilloscope here. I actually tried a couple of different things. I did a logic analyzer with the Arduino as well, and I was able to see all these different signals, but I couldn't analyze them to give me any data. Well, I just spent about an hour trying to shoot this next piece of the video, and why did it take so long? Well, the reason was the servo here kept cutting out. I thought the battery was flat, but it turns out that it wasn't the battery cutting out at all. It was that this little connection here, every time it moved slightly, it was disconnecting the power to the servo. So that was a bit of a problem. So this is the connection that came in the Siku Control 32 tractor. So if you're having trouble with your servos in your tractor, it's probably worthwhile giving the wires a little twist when you're testing it to see, is it just this connection that's failed? I don't know why this connector failed. I mean, it looks fine, but I haven't done too much with this, so I mean, I haven't moved the connectors around, and I've only disconnected it maybe 2 times or 3 times. So, you know, it may be just a crap connector. So if your model has trouble with a servo not working, it might be worth your while to just get the wires and kind of shake it a bit. So the connectors in the Control 32 models might just be kind of crap, so that's no use to us anyway. I rewired this, and what I've been trying to say for the last hour is that now that we have all these parts, the first thing that I learned was that we don't actually need the battery. The VCC wire that goes to the servo is the common VCC wire, which is connected directly to the battery, and there's nothing special in the battery. So I just connected the VCC and the ground to one of my battery packs. In this case, it just happens to be this John Deere mower. So it's a fairly big battery in that. So that's what I've been using for the testing here. And you can see there we're at 3.87 volts. So that battery is fine. This is the only Siku Control 32 battery I have, so I can't be tricking you in any way. This is hooked up to just a normal LiPo battery. There's nothing special about anything I've done here. I've just connected the battery directly to the Siku Control 32 control board, and you can see the steering servo is working fine, and drive motor is working fine, so everything is working perfectly. How that helped me was, you can see the contacts on the back of this are just flat, and there's a spring contact on the other side, so I would have had to all the time hold the battery to the board to try and do the testing, which is pretty annoying. So once I knew I didn't need that battery, I was able to hook it up to a bigger battery here and just wire directly into the board, so that I didn't have to hold the battery to the board all the time, which is very useful. So next thing is to check out our signal wires. So if we take our oscilloscope probe and we probe what I thought was the data line, you can see that we have some data. And if I zoom out a bit, we can see that it is a repeating group of pulses. And we'll have a little zoom in on the pulse here. So I'm calling it a pulse, but it's actually a group of 9 smaller pulses. And what I very quickly noticed, when you move the potentiometer here, you can actually see that each of these little pulses is going smaller or wider, but they always stay in one of 2 widths. So there's always 9 pulses, and the 9 pulses are always 2 particular widths. So I think it's 12 microseconds or 20 microseconds, and you can see that they change as you rotate the pot, and that to me looked like a byte of data. So I think there's one pulse is like the flag to say the data is coming, and then the next 9 pulses, because the first pulse doesn't seem to vary when you change the pot, but the other pulses do, and they seem to vary as if it's a binary counter. So it's maybe going from 0, that looks like FF actually, that's probably 255 that way, down to 0, something like that. Or I'm not sure which way it is, but it looks like it's just a binary value after this initial kind of flag pulse. So that's very useful information. It's not very hard to generate 9 pulses using something like an Arduino. So I've zoomed in to the first 2 pulses here, and I'll just show you what I meant about the pulse width. So we always seem to have one of 2 states. So here's one of the states. So this would probably be a 0. Looks to be about 15 microseconds there, and the gap then is around 150 to 160, something like that. 1408 there it says. So that's the gap between the bits in the byte, I guess you'd call it. And then this it would probably be a 1, because it's wider. That's about 21 microseconds. So what we need is 9 pulses separated by about 150 microseconds, and we need around 15 microsecond pulse to indicate a 0, and a 20 microsecond pulse or 21 microsecond pulse to indicate a 1. So that's what I tried to replicate on the Arduino. That's the line I thought was the data, so that's pretty good. That's kind of what we expected, some sort of a string of pulses. And the next line I thought was a clock line, so let's bring our probe over and we'll have a look at the clock line. But now we have a flat line, so that's not a clock signal. There's no clock signal there at all. That's connected to ground, so that's 0 volts. So then my thinking is, if that's not a clock line, but it's connected to all the servos, the next most likely thing that it is a signal to put the servos into sleep mode, so that you're not wasting battery power when the servos aren't needed. So if the controller isn't connected to the tractor, maybe the microcontroller that's on the main control board tells all the other microcontrollers to go to sleep. I've disconnected this wire from the main controller now, and here is a wire that I'm going to use. It's connected to the other end of this orange wire, the part that was connected to the servo. So if this wire really is a signal wire to turn the servo into a sleep mode, then it would need to be pulled high on the servo board so that there was no mistake. If the servo doesn't get this 0 signal, it will pull itself high to make sure that it is going into sleep mode, that there can be no mistake. I mean, the wire isn't left floating is what I mean. So if I'm right, this should be a positive voltage. And there you go. So the wire is getting pulled high, and with the wire, with this pin, this sleep mode pin, I guess we call it, that's pulled high now, and we have no servo control. We do still have control. We are still connected to the board. So that's the motor there, the main drive motor spinning, no problem, but no steering. That's because the pin has been held high. So if I connect this to ground, so now I have physically connected it to ground myself, so I've imitated what the microcontroller on the main control board is doing, and once again we have connection to the servo. And just again to confirm it, I'm connected, the scope now is connected to that pin that I think is the sleep mode. So I'm gonna plug in the power for the board. If it is putting the servos into sleep, we'd expect it to go high because the controller isn't turned on. So here's the power, and the pin went high, so that's good, we expect that. And now that's the controller is on, and if I go to channel 1, the signal line just went low, so that has taken the servos out of sleep mode. So that hopefully confirms that that pin just puts the servos in and out of sleep mode. So now to recap what we've learnt. If we take a look at our servo, we can see this is the other servo from the John Deere 6920S, and the wires are a different colour. So I can't just tell you that whatever colour of wire equals ground or positive, because they're different. See, there's a green wire here and there's blue in here, but the other three seem to be the same, so maybe you can take that to be the case, but I wouldn't just be that I wouldn't just jump to that conclusion. But the 4 wires are going to be in this order even if they're not this colour. So if you can identify the ground wire, which is going to be on the outside, then the next wire in is red in this case. That is going to be your VCC signal. Then the next wire is going to be the one that puts the servo into sleep mode, and then the outermost wire is your signal wire. If you don't want to switch the servo from sleep mode to awake mode, I guess, all you have to do is connect the orange wire to the brown wire, or that's connect that pin to ground. So you could connect those 2 pins and just have 3 wires coming out. But it's not the same as a normal servo. A normal servo doesn't have 9 pulses. It only has it's a pulse width modulation thing. This is taking actual data. Okay, so I thought the best way to generate these pulses was going to be to make a library that used a timer. So I chose to use timer 2, and I have just made some code that will produce the 9 pulses that we need to control the servo. Now you can see there's a little bit of jitter in the servo there, and I'm not entirely sure what that is, but because I've made it in a library, if any of us use the code from the library, or to use the library in our code, and I come up with some way of improving that, or someone else comes up with a way of improving it, then all we need to do is change the library, and all our other code will just work immediately, rather than having to go through all the code to change the servo part. So we just have to change the one library rather than having to go through our individual Arduino sketches to improve it. So I hope that makes sense. I think it will make things a little bit easier if I do it that way. So with this library, what I've done is recreate the servo library sketches, the example sketches from the servo library. So the first one I have here is the knob sketch. So we have the potentiometer here. We change our potentiometer and that changes the position of our servo. So that's a fairly normal example for a servo. So I'll do the next obvious example, which is just the sweep sketch. So when you download the library, both of these sketches should be in the examples folder of your Arduino IDE. Here's the other example sketch. This is the sweep sketch, so it just sweeps from 0 to 180, but for some reason the servo doesn't seem to go from 0 to 180. It seems to go from about 0 to 150 degrees or something like that. I'm not sure why that is, but that seems to be the way it is. I can't seem to get it to go any further than that. So maybe those limits are set by the control board some way. I'm not sure. So my library seems to be working okay. So the next thing I'll show you is the Control32 servo library working alongside the normal hobby servo library, just to show you that they will work together. Okay, now I've made a sketch that's going to use the normal servo library, which is running this normal hobby servo, alongside my library that controls the Control32 servos. So this one here is the Control32 servo. So now when I move the pot, you can see both servos are moving without any problem, and that's because it's doing one measurement from the output of the potentiometer and it's just writing that value to both servos. So now you can see we can use both servo libraries with each other, because the normal servo library is using timer 1 and my servo library is using timer 2. So with any luck they won't interfere with each other too much. So if you liked that video, don't forget to hit the thumbs up and share the video, all of that stuff, that helps a lot. And as I said at the start of the video, if you're looking for the library for this, there's a link in the description which will bring you to the website, and you can download the library and you just install it like any other library for an Arduino that you've installed before. I'll revisit this in the future, because now we're controlling the servo, but we might also want to add additional functions to a model. So say not all the servo sockets on the control board of the RC tractor were used, so maybe we'll take that signal and we'll control an Arduino and control maybe just another servo, or maybe we want to control a motor. You know, there's a lot of different things we could control using that signal. I'll probably add to this library and include code that will just take the signal from the Control32 main control board, I suppose you'd call it, and just give you a value between 0 and 180. And then once you have that value in your Arduino, you can do whatever you want with it. You can control a servo, you can control another motor, you can do anything with that then. But that's all I have for today, so thanks very much for watching.